When we left off in class, we were just about to do this example where we were going to find the derivative of f of x when f of x was equal to the square root of x. Had a little change of heart. I think it's good practice for you to try this on your own. You're going to use the limit definition. You're going to write up an expression which must include the limit as h goes towards 0 to try to determine a function that contains the letter a for the derivative of the square root of x function. I'll give you a hint. When it's time to try to simplify the limit, you're going to use that third technique that we talked about, rationalizing the numerator. So you're going to have to think of a binomial that you can multiply top and bottom of your fraction by that's going to make it so you have no radicals left in the numerator. If you want to check your notes from 2.1, there are two really good examples there on the last 2 pages. All right, so something that might have come up in class. Sorry if we missed it. This notation we used, we said dy dx might stand for the derivative of a function y. So I just want to point out that dx does not mean d times x. They're not two separate variables that are getting multiplied. Dy doesn't mean d times y. Dx it's one idea, and it means a very, very, very small change in x. So think about the delta symbol we used to use. The delta y divided by delta x, a small change in y divided by a small change in x. That d is like, let's let that small change get so small that it's infinitesimal. So dy means an infinitely small change in y. Dx means an infinitely small change in x. And this notation dy dx altogether, it doesn't mean divide a dy by a dx. It's an expression that means an expression for the ratio of an infinitely small change in y compared to an infinitely small change in x. Same idea with the f notation. Df dx does not mean that there's some number df and we're dividing it by dx. It means we have one whole symbol that means I'm going to compare a small change in the output with a small change in the input. This is an example that is not on your notes paper, but I'm going to use it to connect something we said in class with the example we are going to do. I hope you got today's big message, which is that derivative means slope. The derivative of a function is a new function that if you input the right x value, the x value you're interested in, you would get back the slope of the original function at that input value. And so a corollary to that, related to that idea, is if I ask you to find the derivative of a linear function, well, derivative means slope, and linear functions have constant slope. All that means is you just need to report to me the original slope. So this is an example just to give you an idea before I switch over to this example from your textbook that we're going to do next. If I have, let's get there we go. If I have some function, f of x, here I have a piecewise linear function. Each little piece, there are 4 pieces, is represented by a line segment. I could find the derivative function by computing those derivatives separately, means finding the slope separately, and graphing them as I have here below. So notice here this first piece of the function, I could find the slope, so that line segment contains the points 1, 2, and 0, 0. I can compute change in y divided by change in x, and I get that the slope is 2. So for that whole part of the domain that was covered by that first piece of my piecewise function, which I think is the interval from 0 to 1, my slope, my derivative, is 2. So you can see I've started to make a graph here of the derivative. So the slope of the top function was 2. That tells me the value of the derivative over that same domain must be 2. This piece has a slope of, is it 1/3? 1/3. This next piece is flat. It's horizontal. That means its slope must be 0. You can see how that shows up as the constant function y equals 0. My last piece of my piecewise function has a negative slope. That's why a slope of -1 specifically. That's why you can see here, I've got graph down here at y equals -1. What's interesting, what I hope you take away from this, is it was easy to find the slopes and therefore the derivatives for the parts like in the middles. Where the line segments connect, we have a fight. We have a limit problem. We have the derivative from one direction, the slope from one direction. Let me clear this off so you can see what I'm talking about. For example, here, at the place where x equals 1, the derivative from the left means the slope as I was coming toward 1 from the left, which we said was 2. Well, the derivative from the right was the slope as I come in toward x equals 1 from the right, which we said was 1/3. And since a derivative has a limit definition, the derivative from the left and the derivative from the right, meaning a limit as I come toward x from the left, x equals 1 from the left and x equals 1 from the right, those limits do not match, which means at that one x value, at x equals 1, the limit does not exist. And since the derivative is that limit, the derivative does not exist. So notice here at the place where x equals 1, I had to leave 2 open circles on my derivative function. Piece 1 of the piecewise function says, hey, the derivative is 2. And piece 2 says, hey, the derivative is 1/3. And they're fighting over the place where x equals 1. If they're fighting, there's ambiguity. We can't choose. Nobody gets to decide, so nobody gets it. No, neither piece of my derivative piecewise function gets to claim the place where x equals 1. So at the place where x equals 1, similarly at x equals 4 and x equals 6, the derivative is not defined. That's why I have open circles at both of those spots. All right, so this problem I'll leave for you to do. Here I have another 4-piece piecewise linear function. You're going to need to figure out the derivative, and you're going to graph the derivative. Each piece is linear, so you're going to find the slope by finding 2 points on each line segment and computing change in y divided by change in x. The question B is what's really interesting, which is where is it that you're going to have to leave open circles because the limit is not the same as you come in from both directions. So they're going to be 3 places, 3 x values that have to get left out of the domain of the derivative. Those are the 3 places where this function is not differentiable.